Hello, everyone. So, welcome to the presentation Securing the Keys to the Future Robust Authentication for Next Generation Vehicles. So, our guests Orell Schwarzbach, Gesa Müller, Fabian Maas, and Carlo Bauer. So, they are students from the US Mannnheim University, and they will present their innovative approach to improving automotive keyless entry systems. They will discuss how combining challenge response authentication with timestamp verification can prevent relay and replay attacks, a concept that is still in its early stages but holds great promise. So, we will soon start. Just to remind some basic points to our guests. So, the presentation will take like 30 minutes, and you are always free to ask questions in the QA session. It's a button that you see on the right menu. And please feel free to put your questions during the presentation. And in the end, we will have time to respond to all of them. So thank you. And so we can start.
So thank you for the opportunity to be a part of this SAS conference here. I will just share my screen. I hope everyone can see it now. Should be perfect. All right, perfect. So yeah, thank you for introduction. Yeah, all of us four are near the end of our cybersecurity bachelor, and Fabian and me are presenting this today. So let's see how far we can get, and I hope we can answer all your questions at the end of it. And I would say let's dive right into it. So keyless entry. We all know that keyless entry is an alternative to these conventional remote key fobs where you need to press a key. You can just go to your car and unlock it without pressing anything, or like you see in this picture, there's a small button where you put your finger to open it. But we get a big problem with widespread exploitation of this feature. And we thought about a solution how we can prevent this. And like Kamal already said, it's a challenge response authentication with a timestamp verification. The thing is, the Automobile Club Germany, ADAC, tested this year in February, I think, a lot of cars. And as you can see here, only 50 out of these 648 tested vehicles, so less than 10%, were really protected and safe. And as we will see later, they are not really safe. They're just safe for this test. So what attacks are we talking about? Oh, we got a replay attack. A replay attack is pretty simple. So you can see the vehicle on the left and the vehicle owner and key fob owner on the right. And then we'll see the thief over here. The thief will intercept the signal the user sends with the key fob to the car, intercepts it, saves it for later, and then will reuse it to just open the car later on when it is at your house or anywhere else. And he will just unlock it with the same signal sent from your key, which he has saved. So there is unauthorized access without the possession of the key. So we don't have to need physical access to the key, just to the signal the send anywhere at the groceries or at your home or wherever you unlock or lock your car. But there is already a solution in newer key fobs and newer vehicles, which is called rolling codes. Rolling codes, as you can see here, we like to explain it a bit because it's important for later on. There's a synchronization between the key and the car. Usually it is not made by the user, it's made in the factory or where you buy the car. The key and the car will be synchronized and you don't have to do anything else. So if you press the button or if you just go to your car and have the keyless entry system feature, you will get into a range of the car. And the key will just generate a code out of a list that is played on the key and played on the car, and will then send the key. So the code is sent from the key to the car, and the key will just take the next code in this list. The vehicle will unlock and will also just take or just want the next code. So as we know this picture from before, with the rolling codes, we are protected against these attacks because I will send code 1, the attacker will get code 1, I open the car, and the car wants code 2 next. But it is not a fully implementation of security because this will just need the thief to do one extra step that I will show you now. So as we can see here, the thief will now intercept the signal and jam your signal as well. So at the same time, he gets your key, he gets the code he needs that is sent for code 1, and the car wants code 1. And sends to your key, yeah, I got the code, you can send the next one. So he waits for the second signal to be sent from the key. The key sends code 2, and the attacker will save code 1 and code 2. Now that he has got both keys and the car is still locked, he will send code 1 to the car because car already wants or also wants codes 1 to open. The car will unlock, and the key will just get the signal, yeah, code 2 works. So we get to code 3, and the car next wants code 2. The attacker already got code 2 stored from the earlier interception and can use it for later on to unlock the car, even with rolling codes. The second problem we get here is that the key and the car, as you can see here with the black arrows, will get out of sync. So even if the attacker won't use it next time, if you unlock your car, if you try to unlock your car, the key can get out of sync because it will send code 3, but the car just wants code 2. So that's the problem, that you often have to go to a repair shop or anything so they can fix it, and you often can't manually fix yourself. So as you can see, there is some kind of implementation of defense, but it's not working for all attacks. And it's pretty easy to just jam it and to get it rolling codes as well. So the second attack we get here is the relay attack. So imagine you're coming home and you're going through your door and just put your key just next to your door. Hang it on the wall where you do it every time, and you just go to bed because it was a hard day. So the thieves know that a lot of people are putting their keys from their cars next to their doors. So what the thieves do, they need two people now with a repeater. One goes to your car, one goes to your door from the outside, and will just hold the repeater where your key could be. The problem here is that those keys are sending all the time. They're sending all the time, and so the attacker can easily get the signal and just put it or send it to his repeater, and the repeater opens the car. If you also got the keyless entry and the keyless go feature, in many cases, the car will get started and they can just drive away with your car um, as far as they can go with the fuel, or as far as they can go until they have to just put the engine off. So as you can see here, the problem is they also don't need any physical access to the key. They just go from door to door, from car to car. They know which car has this feature. They know which car they can attack with this relay attack, sorry. And they will just use it. And yeah, maybe they get one or two cars at night, and it's a big profit for them and not much for to do. We got also, I guess, yeah, we could say two features from the OEMs that work against this attack. The first one is a pretty new solution. It's pretty simple, but it's good. The motion sensor deactivates the key after some minutes. So you hang it on the wall, the key won't send anymore after 2, 3, 4, 5 minutes. So any attacker walking from door to door can't extend the signal and won't open a door. The problem we get here is, at first, only newer keys got this feature. And the problem we have here also, if we remember the ADAC test from the beginning, these were the keys that were labeled as safe or as secure early on, because they just hang it on the wall. They put it there for 5, 10, 15 minutes, and they couldn't use it. So this was safe for the Automobile Club Germany. The second solution for older keys is a solution that the car owner has to get rid of the problem by getting a Faraday cage. So you put your key in a Faraday cage, and what a Faraday cage does is it cancels out the field effect inside the cage. So your key won't send any signals outside. Um, and yeah, you're safe against attacks. There are also some small pockets where you can put it in and you can carry it with you all the time. But if you carry it in those pockets, you can't use your keyless feature as well. So yeah, you don't have to pay for it if you don't use it. This is no real solution for us because it's cheap for the OEMs, but it's not comfortable for the user, and it's no real solution to have to put your key inside this Faraday cage all the time. And if you forget it or anything, your car can get stolen. So to get to the basics of our concept, we want to, in the first step, we want to measure the time needed to send a signal between the car and the key. So the problem we have here is that we need a precisely measurement and get pretty accurate sync between the car and the key fob, which is nearly impossible. So we thought, okay, how precise do we need to be? We don't need to know if it is 1 or 2 meters away. We need to know the difference between 5 and 20 meters or between 5 and 10 meters. So our solution is, first of all, we thought, why would the key be sending all the time? I mean, let the car send it. The car got a lot of more better more power, better hardware, and everything. So we would like to let the car send the signal first and not the key. And the precise or the more detailed explanation how we want to do it will be shown by Fabian later. So relay attacks are no problem with this solution, but we also got those replay attacks. And for those, we need to be sure that the attacker can't hear us and can't use the signal against us or to open the car. So the simplest solution that we got through is just encrypt the message between the vehicle and the key fob. So he can hear it, he can intercept the signal, he can still jam us, but he can't use this intercepted signal later on, and he don't know what we are sending. But if we're sending the same thing all the time over and over, he can just use the encrypted message and open the key later, the car later, sorry. So what we're trying to do is we will not just encrypt it, we will also send a random challenge every time the key and the car act with another. And these random challenges will change over and over and over again. So it's random challenge every time. Even if the attacker gets challenge 1 and also the solution of it, he can't use it later on to open the car. He can use it to open the car right now, but that's what we want to do. So yeah, he won't do any damage. And yeah, he can't do anything with the information he got because the encrypted message won't get away. What was the challenge and how we saluted it. So this is our concept, the basics of our concept and the basic of the attacks that we know of and we want to get rid of. Now Fabian will show you a bit more technical and a bit more detailed how our idea works. I will stop presenting now. I hope, Fabian, you can share your screen.
Yes. So thank you, Orell, and I will share my screen right now. So I hope everyone can see it now. And yeah, you already might think, or you already might guess, okay, what does the technical implementation look like? And we prepared a sequence diagram for you that shows a little bit how the communication can work. And on the left side, you have the car, and on the right side, there's the key. And as you can see here, we have also a handshake on the in the top of the communication, and we decided to do a handshake because we don't want to always send the encrypted message. So the car doesn't need to create a challenge, encrypt it, and send it to everybody near around. So that's the reason why we say, okay, let's do a handshake before that the key and the car, they should know each other before. Like you could use like public public encryption for this, public key encryption um, for identification or something like that. And yeah, for the handshake, it's basically that they know each other then, and then can start with the challenge. So then you don't have to broadcast always the encrypted signal. And what's also important here is that the key is not starting the communication, the car is starting the communication. That's a really important thing because it makes more sense from our perspective. And the key can also then just receive this message and start working on it. There could be like a technical solution like RFID. There is like passive RFID, but we're still in the early stage. It's just a concept, so that needs to be decided. But first, we now get to the next points here. So we get a little bit closer to the upper part, and now we're going to have a closer look to the encrypted part. So as I said, the car starts with creating a challenge, and it create a timestamp. It will encrypt this message and send it to the key. Which type of encryption will be used? Like I said, it depends on what we want to use, what we want to achieve, and what's the best solution for it. May it symmetrical encryption, asymmetrical encryption, or hybrid. Yeah, we still have to figure that out. But at the end, the message will be sent to the key encrypted. The key decrypts the message, solves the challenge, and encrypts again. This challenge itself should not be too hard, that it's not like it doesn't need too much CPU power or what else. So it needs to be really quickly solved, but it should be also not too guessable or easy guessable that the adversary or the attacker cannot guess the encrypted part and just can copy that and use it for the car. So you need to have like a perfect balance between too hard and too easy. And after this challenge, after this challenge is solved, it will be encrypted again from the key, will be sent to the car, and the car decrypt it's of course, and then will calculate a signal round trip time. And with the signal round trip time, it can determine the distance to the key. The distance to the key is basically a time, and in the car there is a threshold set, and this threshold basically means if the distance is lower than the threshold, the key will be accepted, and if the distance is higher than the threshold or the same, the car gets rejected because it's too far away. And yeah, with this solution, or first, this is the distance measuring, and after that, of course, the challenge will also be verified that everything in the challenge is working. We did it that way because we first said, okay, if the key is not in range, why we have to verify the solution. I mean, if it's not in range, just don't open the car or don't look at the challenge at all. And now we're going to have a look at the attacks a bit. Already mentioned by Orell, the relay attack. And you can see here between the car and the key, there's the adversary who tries to bridge the distance. And there is a check mark, as you can see on the handshake. It basically represents a little bit the communication to make it a little bit more visible. And of course, it starts with the handshake. And the handshake is in that part not so relevant, but now we come to an encrypted part. So the car will send all the messages to the key and back. And as you can see here, this is the first part, and then it goes back to the car. And of course, if the distance is too high or they are too far away from each other, then it will just be rejected, like I said before. So it's pretty straightforward with the relay attack. And with the replay attack, it looks a little bit different. So same sequence diagram, but now we have a C1 here. C1 is basically the first challenge we will use. and the car will create that challenge and send it to the key, and the key will do all the things like solving the challenge and so on, and then the adversary will intercept that C1 and will also jam the signal, like Orell already mentioned. And then, of course, the car will resend another challenge because the first challenge wasn't received after a few seconds. Like we see on the left side, it's at the moment 1 second, but that could change depending on what we see in the test. So in the implementation phase or in the prototype phase, we would see if 1 second is enough or we have to go down or up. And like I said, the next message will be sent. And then you see C2 will always also be stored by the adversary, and then the adversary will send C1, like with the rolling codes, basically. And C1 and C2 are crossed here, so they are not longer valid because in our scenario, only one message at the time will be valid, of course. So if the C1 is sent and it will and the C2 will be generated, already then C1 will be not usable anymore. So that's basically it. And as you can see here, C3 went straight through because the adversary, I don't know, maybe he just don't want to intercept this one or went away because this wasn't working. So C3 went through and the car basically opens. And we thought, okay, what do we need to be aware of? Especially for the measurement of the distance, we thought, okay, we are using radio frequency here, so we are basically sending with the speed of light. That means we are with one way, if the signal needs to travel 5 meters, we are around 17 nanoseconds. And this is just one way. So if we double this for the way back to the car, we have like 34 nanoseconds around that. So as you can see, we need to be really, really precise. And therefore, we need to make sure that the CPU or the processor in the key and the car, they can handle this, and also the frequency can handle it. So this is the reason why we did a little bit of a research, and we come to the conclusion that there are basically 3 solutions possible. Maybe there are more, but for us, these 3 solutions would make the most sense. And the most important parts here in this matrix are basically the accuracy and the latency, and the ultra wideband, so the left column, is basically the one which could be the most potential one because it's already in use in some other cases with similar strategies. And as you can see, the accuracy here is around 40 centimeters. The latency is under 1 millisecond. So this could potentially be used for our scenario. But we have open challenges because we are still in an early phase. So it's like a really basic concept at the moment. And that's the reason why we need to do a proof of concept, of course. So we need to test if the accuracy is right. We need to make sure that the numbers, that our parameters are working good. And that's the reason why a proof of concept is definitely needed here. As I said, the measurement of the time needs to be in nanoseconds. So we need to make sure that the software is able to deal with that. Because of course, if you want to go to your car and have to wait like 10 seconds that it opens, it makes no sense. So usability and security need to go hand in hand here. And of course, what I also already said is the cryptographic algorithm need to be determined. So what is the best algorithm that can be also like be chosen in a proof of concept, of course. Yeah, so we are already almost at the end of our presentation. So thank you all for participating, and I hope you enjoyed it, and I hope you have some questions, and we hopefully can answer them. And this is just a quick overview of our solution. So we thought it makes sense to do some kind of approach because there is a high volume of car thefts due to this unsafe carless entry. And as you heard from Orell already, there are no real technical solution at the moment. Maybe they are working on some solutions, but I think, or from our perspective, it's always better to have more options, to have more research, so they can basically pick from a good research and develop on that. So it's always better to have more solutions than less, I would say, or we would say. And yeah, it's a technical approach on this thing, because at the end we are coming from an IT technical background, and I think as a person with a technical background, you don't want to put something in a Faradayfical cage. So that's a little bit like going back in the time. So yeah, that's the reason why we did this. And of course, we need to test and determine all the details on this. So I think you enjoyed the presentation, and I'm happy to read all your questions. Thank you.
All right. Well, thanks for the presentation. So we have many questions piled up. So I see the subject is quite interesting for everyone. So without losing time, so I would like to take on the scene the questions with order of voids, because the voided questions appear first on the line. So the first one is, usually in passive entry, passive start systems, the detection of the fob presence in the car to enable engine start uses the LF 125 kHz signals. In order to relay such frequencies, the attackers need huge antenna that is not practical. Okay, so I don't know if the question is clear for you. So if you got the question, please go ahead.
Okay, I think, sorry, I just would like to, try to answer it. So if I read it right, it's especially for enabling the engine starts. So it's not a keyless entry, it's keyless go feature. We heard about it. They use different different signals, different different frequencies. That's why we only focus on keyless entry first. We can't really tell you if it is practical or not, and if we can defend against this. But I hope this answers the question as good as we can.
All right. Thank you. So the next question is, could you explain in detail how the handshake before encrypted messaging looks like?
Fabian, would you like to explain it, Fabian?
So yeah, actually, it's not 100% sure at the moment. So we thought a little bit like we do it with like a TCP handshake. Or a SSL handshake, depending on what we want to achieve, basically. So that's also one part that needs to be determined in a proof of concept, of course, because we thought it would make sense just from the standpoint that the encrypted message will be not sent always, like everybody in the near distance can see this message. I mean, it's encrypted, of course, but depending on what encryption we use, it's not possible, or it could be also used for cracking the algorithm or something like that. So it really depends what we want to achieve, and it needs to be determined in a proof of concept, I would say.
All right. Thanks, Fabian. So we jump into the next question. Have you also looked into existing digital protocol and standards like CCC digital key and see how it compares with yours?
I think we can answer this short. We haven't. So we haven't looked into digital key protocols. We just use normal ones in our statistical approach. We haven't looked into anything practical right now, and we haven't tested really. That's why also our times and timestamps that we put into the presentation needs to be tested more. If it is even possible with the 17 nanoseconds to send it, if we can get more seconds, if we can put our delay a bit more, because the key and the car needs to process it, and yeah, that needs to be tested in the fields.
All right, thank you. So the next question, so this one is answered. Does encryption add a major delay to the functionality of the key fob? And if yes, have you thought about clever timings on when to perform the encryption and decryption?
I can answer this one. Yeah, so we thought about this one. This is also one thing we we thought about because yeah, so we are basically doing this in nanoseconds, or we think it's in nanoseconds at the moment. And of course, with every layer, with everything you potentially compute in the process, of course, you get there will be a higher delay, or there will something like added to this nanosecond. So depending on what we do, like if you do, of course, asymmetrical, it has a higher compute cost than a symmetrical encryption. But with the asymmetrical encryption, you have also like you could use the public key as an ID for the handshake or something. So yeah, we thought about that. But we're not sure how to optimize it or what to use. Like early stage at the we are really at the beginning. So yeah, in a proof of concept, that would be really nice to know what we would do with that one. Yeah.
Thank you. So it takes some time to questions to refresh. All right, based on what information does the car trigger the handshake signal?
Yeah, that's a good question. Yeah, I think I have to answer this with the same answer basically. So it really depends. So we are really with the handshake. We just thought that it makes sense to have a handshake, to be honest. But yeah, the thing is, I said, and that could be a potential solution, is like passive RFID. So I'm not 100% sure how that works, but I know that it exists, that you have like a RFID tag in range of a RFID um, yeah, transceiver. No, it's standard transmitter, uh, and they enable a connection based on that. But the passive RFID tags are really, really stupid. So they are not really doing anything. They do not calculate or have to calculate something. So it depends. Maybe it can be used or it cannot be used. So this also, yeah, we need to do a proof of concept on that as well. Definitely.
Yeah, our second option would be that like the key is standing all the time, the car would be standing all the time, but we would like to avoid this if possible.
All right, so we skip to the next question. BLE or UWB messages, even the shortest one, is longer than 17 nanoseconds, which means they are not suitable for range tests.
Yeah, I would like to answer this. Yeah, we know that we need a lot more timing, and those 17 nanoseconds were just to show that we need to be precise for to calculate if it's 5 or 10 meters away, and the 17 nanoseconds were just the sending time from key to car. So what comes on top of this are the time that the key needs to calculate and to get a solution of the challenge. and for the car as well to just determine if the challenge is saluted correctly or not. So this will, of course, need to get tested, and we would test if it's 5 or 7 or 8 meters away, and at 5 or 20 meters, what we really need as time to send. But we need to have a lot of, or the smallest possible time needed to be sent between 1 and 2, so car and key. That's why we said UWB, sorry, has 17 nanoseconds, well, it's the best in our case right now.
All right, thanks, Orell. So we still have time, so I'm going on with the questions. I hope you are all fine, not too tired.
We are fine, absolutely.
Okay, perfect. So how do you propose keeping encryption decryption key secure on the key fob itself?
Yeah, maybe I can answer that. So, yeah, so that's depending. So there could be like an approach that we do it like with a chip that is securing something, like on the iPhone. The iPhone has like a controller or a microchip that enables this secure hardware and storing keys and stuff like that. But like we still talking about a key, so you don't want to at the end have a phone for a key. That's not our approach. So what we thought is like, if the key is not say it's like you can everything read on the key itself, like if it's open, if you crack it open. I mean, in the end, if you have a key, if you get a key, you have the key. I mean, if then you don't need to extract something. You have the key, and then you can open the car. That would be the other approach. So yeah, it's also depending on this in this one. Depending, not appending. Sorry.
Thanks, Fabian. So the next question. It seems to be mine. Well, the keys generally have small batteries, and in this communication scenario, will the battery last sufficiently long, or will be just depleted within days? So what's gonna happen?
Yes, so we try to have the most communications sent by car, and so the most power usage will be, most power consumption will be by the car. So it should last sufficiently long, but that has to be checked and tested in a POC.
Thanks, Carlo. We go on with the next question. Yes. So what is the benefit of encryption? Encrypting the car key communication only to secure the timestamp? Because no replay attack seems possible since car will generate a new random challenge each time.
Yeah, I will try to answer that. So I thought about if we don't encrypt the current key communication, of course, we need to secure the timestamp so that no attacker can manipulate it and just use it. So it says, yo, later on, so I can use it over 20 or 30 meters. That's, like you said, the first thing. But the second thing we need to be sure or be sure of is that those challenges, the attacker shouldn't intercept it, even if the car is sending it all the time. So if you don't have a secure communication, not only the key can resolve this communication or resolve this message, even an attacker can. So that's why we want to be secure there and encrypt these communications between those two. So I hope that answered it right. Yeah.
All right. Thanks, Orell. So we jump to the next question. All right. So, well, it's again a question from me. If the person is walking or running towards the car with the key, is there a possibility that the vehicle might get confused due to Doppler effect, but needs to run really fast, I think?
yeah, first you need to run really fast. And yeah, the problem we see here is the worst case that happens is the car won't open. So you can't use your keyless feature this one time you are running to your car. And you have to use your normal key and open it with the button on the key that is still there. So yeah, you can't use the keyless feature. But what won't happen is that the key will just open and say, yeah, it's okay, you're fine. So yeah, I hope that answers your question. Because everything else, if it can happen and what timing we need to send again and again, the challenges and how often, yeah, need to be tested. I'm sorry.
Yeah, yes, of course. Well, thank you. Thank you, Orell. We continue with the questions. So, have you encountered vendors that implemented range measurement?
I would like to answer the question. So at the beginning of the presentation, Orell mentioned the report from the German Automobile Club, and they actually found out that multiple vendors, for example, Volkswagen and Skoda, they use UWB to measure the range between the car and the key. And if it's too long, if it's like an illegal range, then yes, the car won't be opened. And we think that's a technology that more and more vendors will be using in the future, as it is a new technology that makes the whole keyless go system more secure.
All right, thank you, Gesa. So we still have 3 minutes to go. Which communication protocol should be used for your solution with encrypted message?
Yeah, maybe I can answer this one. That's a hard one because in the early stage we thought about it should be like some mathematical equation that is not too hard to calculate, something like an addition or something like that, so you don't have to add two numbers and then you get a result. The results will be returned to the car and the car says, okay, that's the result I expected. So it's basically just mathematical equations. But yeah, maybe there is some better approach on this one. Maybe there are like well-established challenges that could be used here. But yeah, that was in our thoughts, it would be the easiest one, and maybe it's also hard guessable. But yeah, needs to be tested. Sorry.
All right. Thanks, Fabian. Apparently, yeah, every system that needs test and proof of concept. So I think it's just normal. So we can maybe take the last question. So, well, depending on the time to answer, have you benchmarked the injected delay using the radio repeaters?
Short answer, no, we haven't. So, yeah, we haven't had time to really benchmark it, and yeah, we use it to open some cars, but we haven't injected delay and benchmarked these.
Yeah, I think your list of to-do things have grown. Orell.
Yeah, it's really big right now. And
Yeah.
after this session here, it's even bigger. So I think we have a long way to do. So yeah.
Yes. Well, I marked this as answered. So it is, well, we have almost run out of time. So I think we should stop here. Just for our guests, now it's break time. So there will be a 10 minutes break. So after the break, please continue with other sessions that will start. And I would like to thank once again to Orell, Fabian, Gesa, and Carlo, where they are students from Mannnheim UAS. So they are not from a supplier or any research company. So they are not paid engineers. So they are students. And I really appreciate and I'm impressed by their fluidity of answering the questions and explaining the technical details of their design. So yes, congratulations, and I hope you success in your future life.
Thank you.
Thank you.
So we are closing this session, everyone. So thanks for the participation. So please take your coffee, but don't go away for the next sessions. See you soon.